Okay, hi everyone. Why don't we go ahead and get started? Welcome to the last session of day 2. This is the first of 2 sessions on cross correlations between the 21 centimeter signal and other signals. My name's Seth. I'm a research associate at McGill University, and I'll be acting as chair. Before we start, I'll just remind everyone that there is a Slack channel for this session at 21 centimeter 2022-2C. If you have questions during a talk, please reply to the message corresponding to that talk in the Slack channel, and I'll make sure it's conveyed to the speaker and answered at the end of the talk. If you are unable to access Slack, we'll be monitoring the chat, and you can also just post your question to the chat, but we would prefer if you use Slack so that it's archived. We'll start with a review talk that will be 20 plus 5 minutes. All other talks will be 12 plus 3 minutes. I'll give a warning to the speakers 3 minutes before their time is up. Our first speaker is Jordan Mirocha, who will give a review of cross correlations in the Epoch of Reionization. Jordan, would you like to go ahead and get started?
Absolutely. All right. So welcome everyone, and thanks to the organizers for inviting me to give this review. So my goal today is to give kind of a bird's eye view of this little corner of the field. I'm obviously not going to be able to touch on everything, but my hope is that, if this is something you're interested in getting more into, that my talk might serve as a nice place to start and dive deeper into some of the references that I'll list throughout. So the plan's pretty simple. The kind of big picture motivation might not be news to a lot of people here, but I'm going to spend a few slides on it anyways, just to make sure we're all on the same page. And then I'll kind of roughly split the rest of the talk between what's kind of going on observationally, and then what's going on in theory land. And I'll try as I go to highlight challenges that might make for interesting avenues for future study and collaboration. Okay. So the big picture here in this corner of the field is the following. So we often use this nice figure from Patrick Brycey to motivate intensity mapping in general. So on the left, you're seeing how kind of a magnitude limited galaxy survey would capture only the tip of the iceberg of the galaxy population in these red points compared to the true underlying distribution in the gray points. And so in sacrificing resolution, using intensity mapping, you can constrain the entire galaxy population using every photon statistically. Okay, so this really motivates intensity mapping as a tool for learning about structures in the universe. In this session today and in the second session on Thursday on cross correlations, we're going to get a little bit greedy. And rather than using this to kind of motivate this whole enterprise, we're going to ask, what can we do if we have an intensity map and a survey? Or perhaps intensity maps at multiple different wavelengths targeting different lines. Okay, so that's kind of the big idea here. If you're coming at this from an autocorrelations perspective in either of these quarters of the field, you're probably used to seeing power spectra that look like the one on the left if you're used to the tracer residing mostly in galaxies. So the structure of this power spectrum is basically 2 components. On large scales, the signal's dominated by clustering, and then we have shot noise that becomes dominant on small scales. If your tracer instead targets the intergalactic medium, like the high redshift 21 centimeter line does, then we expect power spectra to exhibit a much different structure. They have these kind of shoulder-like features that emerge as reionization progresses. Okay, so if you have galaxies in the EOR being traced by some line and 21 centimeter, obviously these two things are going to have some astrophysical parameters in common. And so you could imagine just kind of jointly constraining the parameters of your model by including these signals at the likelihood level. That's not what I'm going to be focusing on today. So I'm going to focus on sort of proper cross correlations where it's assumed that the 2 data sets being combined share overlap at least a little bit in their sky coverage, their redshift coverage, as well as their Fourier mode coverage. And I'll say more about that later in the talk. And as Seth alluded to, I'm going to focus entirely on the high redshift 21 centimeter background and leave the low redshift stuff to people who are more qualified to talk about that than I am. Okay, so why cross correlate? So it's been appreciated for some time now that cross-correlation is a really valuable tool for getting around some problems with foregrounds and potentially systematics. Okay, so you can imagine if you have two fields, A and B, that are some sum of the signal you're interested in, some foregrounds here and some noise, and you're interested in computing their cross spectrum, okay? That's gonna be related to the ensemble average, probably in symmetrical K-space of the Fourier transform of both of these maps. I'm being a little sloppy with notation here. I hope you can forgive me. And the Fourier transform is a linear operator, so we can just expand out all of these terms. And you see that we have kind of the thing that we want here, which is the cross spectrum of the true underlying signals of interest. And we have a bunch of stuff that we don't want, involving the foregrounds, the noise, and cross terms of the signal with each of those things. So you can imagine in a special case where we're calculating the auto spectrum and A equals B, a term like this is going to be very large. So the foreground for one signal is going to be very correlated with itself. But if A and B are probing very different signals, different wavelengths with different experiments, this kind of a term could be much, much, much smaller. Okay, so that's the basic appeal of doing cross correlations as a way of testing whether we're seeing something at high redshift or not. Real life is always more complicated, and we're going to hear about that from Hannah later this session. Okay, so the second big motive is that cross correlations open up new windows into reionization in galaxies. So these plots are from Adam Woods' 2009 paper. What you're seeing here on the left is a Mach 21 centimeter map. The dark regions correspond to ionized bubbles, and the reddish regions correspond to an IGM that's been heated well above the CMB. And on the right-hand side, we're seeing the galaxy density field. And you can just see right away by eye that regions that are overdense in galaxies are dark at 21 centimeter, redshifted 21 centimeter wavelengths. This makes sense. We expect galaxies to drive reionization. And so we're kind of to zeroth order expecting there to be an anti-correlation when we cross-correlate a galaxy population with a 21 centimeter map. So you can do the usual thing and calculate the cross spectrum, the dimensionless cross spectrum in this case, between these fields. But often what people do is to focus instead on this cross correlation coefficient R, which just recasts things into the nice -1 to 1 domain. And here, a few things are noteworthy. Okay, so at very early times, when the ionized fraction is small, these two fields are correlated with each other on large scales. But as reionization progresses, we develop a strong anti-correlation, as we were expecting from the previous slide, between galaxies and the 21 centimeter field. Okay, and as reionization progresses and the bubbles grow, the scale at which these two fields decorrelate grows as well. Okay, so in principle, by measuring the cross correlation between these backgrounds, we can learn about astrophysical parameters. Okay, this depends on how we select galaxies, but we can also learn about reionization by watching how this kind of decorrelation scale grows with time. Okay, so this is a really interesting way to look at the ER in galaxies. Depending on what line you're looking at, though, life gets more interesting potentially, but also more complicated. Okay, so we have many potential tracers of high redshift galaxies to choose from. So we're often familiar with thinking about things like Lyman alpha, which probe star formation, or H alpha, relatively cleanly. But for example, we might also be interested in cross-correlating with far infrared lines, like carbon 2, oxygen 1, oxygen 3, and so forth. So these lines are different from the kinds of lines we're used to thinking about, as they more directly probe the properties of the interstellar medium in galaxies. So whereas we might be used to thinking about the metallicity and the way that it influences the kind of ionizing photon production efficiency of stars, now we're directly sensitive to the metallicity of the interstellar medium, as well as its temperature, its density, how neutral it is, and so forth. Okay. So this is a really exciting window into the interstellar medium of high redshift galaxies. It's also a potential complication. If you want to use cross correlations to learn about the cosmic star formation history, you probably need to know at least a little something about how luminous individual lines are as a function of star formation rate, and that can be very difficult to model. So what you're seeing here are a variety of predictions for the relationship between star formation rate and line luminosity for different far infrared lines. And these are coming from Pelletini et al. These are the SARA simulations. You can see there's quite a bit of scatter in these predictions. And there's quite a bit of scatter as well in how different galaxy populations at low redshift seem to occupy these spaces. Okay, so this is a potential complication. But if you don't care about inferring interesting things about the interstellar medium of galaxies, cross correlations still might be really interesting as a way to validate.
Sorry, Rahul, could you mute? There's a lot of background noise. Thank you.
Yeah, thank you. And so recently it's been appreciated that by measuring the cross correlations between a number of lines, you can actually infer the auto spectrum of one line of interest. So the example being shown here is, imagine you have, you're interested in validating a high redshift 21 centimeter power spectrum detection, or make a prediction for what that ought to be. If you have two other lines to cross correlate with, you can use the relationship between, you can use all of these different cross correlations to infer the auto spectrum. So this is pointed out by Bean et al. In 2019. Lisa McBride has also been thinking about this very recently, and is showing that even in situations where the bias that you constrain on each individual, from each individual line, even though those might be non-Gaussian in general, you can infer a relatively Gaussian PDF for the 21 centimeter power spectrum. So there's a potential bias here. Lisa's still trying to identify the origins of this, but I encourage you to keep an eye out for her paper that should be out soon. Okay, so what's going on observationally? So I alluded earlier in the talk to the fact that cross correlations are going to need overlap in redshift, their case-based coverage, and also their coverage on the sky. So I've just chosen a handful of examples here to focus on. You can see versions of plots like this out in the literature. But I thought it'd be easiest just to look at, as a function of redshift, what lines are being targeted by a handful of upcoming surveys, including near-infrared surveys like the SPHERICS Intensity Mapping Experiment, JWST NIRCam, the Roman Space Telescope, as well as HSC and Fred Young Submillimeter Telescope on the ground. Okay, you can see that while H alpha reaches a little bit into reionization for a number of these probes, Lyman alpha is sort of the strongest and main target of interest in a lot of work in this field, as well as carbon too. Okay. So as always, as has been appreciated for some time now, though we have nice coverage in cross correlations of 21 centimeter in Lyman alpha and carbon 2 in redshift, the case-based coverage of 21 centimeter experiments is not an ideal match for galaxy surveys in particular. So as many of you I think know, a 21 centimeter experiment like Hera carries most of its sensitivity to modes along the line of sight rather than in the plane of the sky here, whereas for galaxy surveys, it's generally the opposite. Okay, so this is potentially a problem, especially if you imagine having to throw away the lower right-hand corner of this space due to foreground contamination, the so-called wedge. But in principle, there is at least a little bit of overlap here, as we'll hear about later. Okay, so finally, one wants to know if these different experiments are actually pointing in the same place. So we've been investigating this a little bit within Hera. Of course, the Simons Observatory is going to cover most of the south outside of the galactic plane. And so any experiment operating in the south could potentially cross-correlate with Simons, as well as SPHERICS, which is all sky. Now, here I'm showing a couple 21 centimeter experiments. So for example, Hera's drift scan stares overhead at a declination of -30 degrees, and the NWA has historically focused on these 3 EOR fields shown in the cross-hatched regions. Apologies to LOFAR and GMRT, which are in the north. And so now I've overlaid a number of upcoming wide field galaxy surveys. So for example, the Subaru Hyper Supreme Cam galaxy surveys are shown in these vertical bars. These are the wide fields. Lyman alpha observations are conducted in deep fields, one of which is right here. And I've also shown the Roman high latitude survey, okay, which is about 2,000 square degrees. And I'm showing the two Euclid deep fields, one of which is about 10 square degrees, and another of which is about 20 square degrees. Euclid will cover this whole area in its main survey, but that is likely too shallow for a successful cross-correlation within the upcoming 21 centimeter experiments. But these deep fields are comparable in their depth to a Roman high latitude survey. And just to orient you a little bit, so there's these famous fields where we have multi-wavelength data for galaxies at high redshifts, like Cosmos is right up here. And then this region down here is the home of Good South, Hubble Ultra Deep Field, and Feist will also look here at a 16 square degree field for its carbon-2 campaign. Okay, so the short answer is yes. Different probes do see the same sky at least a little bit, so that's encouraging. So now let's jump into what we expect to see. So the best case scenario, I think, is not surprising in the future with something like the Square Kilometer Array and something like an HSC Lyman alpha emitter survey. 21 centimeter Lyman alpha cross correlations are a slam dunk. Okay, so what you're seeing here are predictions from a recent paper from Verdanek et al. And the main thing of note here is the shaded regions, which are indicating the spread over 10 mock observations, show that you can constrain in quite a bit of detail both the K dependence of this cross correlation coefficient, at least at two different redshifts here, redshift 6.6 and 7.3. So the question I'll address for the next few slides is, can we do something sooner? Okay, and we'll hear more about this in other talks in this session and on Thursday. Okay, so people have thought about this on the MWA side of things, again, using an HSC like Lyman alpha emitter survey. And right away, you notice that the error bars are much, much larger, especially as you go to small scales. But on large scales, one can in principle imagine constraining this cross-correlation coefficient well enough to discriminate different astrophysical scenarios, which are the solid versus the dashed curves here. Again, at a couple different redshifts for a 5 square degree field of view. So that is encouraging. I would encourage you also to stick around for Paul LaPlante's talk. We'll talk about a similar exercise considering Hera and the Roman Space Telescope. And then on Thursday, Ian is going to tell us a little bit about what we can learn from cross correlations very late in the EOR. Okay, so we talked about galaxy surveys for the last few slides, and we know that intensity mapping is potentially a very efficient tool for catching Lyman alpha from high redshift galaxies. And so maybe something sooner is possible with SPHEREx. Okay, so this has been looked at by a few authors recently. The plot I'm showing you here is from Cox et al., where the authors found that for the kind of nominal SPHEREx sensitivity numbers, cross-correlation with Hera is not looking terribly promising in the near term. However, if the depth were to be increased and the foreground mitigation scenario is more optimistic, you might expect a couple sigma detection in the middle of the EOR where the signal peaks. However, things look a lot better for CDIM, the cosmic dawn intensity mapping, cosmic dawn intensity mapper, which is kind of a successor to SPHEREx in the concept stage now. So here we're looking at more like 10 sigma-ish type detections well within the reach of a Hera cross correlation. So SKA cross CDIM is very promising in the long term. I'd encourage you to check out these papers for predictions on that front. Okay, so I guess what I'll call proper cross correlations are very difficult, as we've just seen. And so in the near term, people have had a lot of clever ideas for trying to get some constraints with the data that we have now. So this plot is one I'm showing from Kath Trott's recent paper using MWA data. And this team took a matched filtering approach to trying to constrain the EOR. And so basically what that means is, we know where high redshift LAEs are, at least some of them in fields overlapping with MWA fields. And so you can basically build a template for what the 21 centimeter background ought to look like if each of these LAEs resides in its own bubble. Okay, and you can allow the properties of the bubble sizes, for example, to change, or the size distribution of bubbles to change. And on for each set of those parameters, build a match template and look for the presence of that kind of signal in your data, which is what these authors have done. And I found that you can actually, place some interesting constraints on the brightness temperature of the IGM outside these bubbles. Okay, so that's one interesting idea. We heard a little bit about stacks yesterday. And in a low redshift context, people have also thought about this at high redshift, where rather than trying to constrain the H1 content on average of the galaxies that you're stacking around, we'd be learning something about the typical bubbles around bright sources at high redshift. So these predictions are for paper from Davies et al. 2021, showing that if you stack around bright Roman high latitude survey selected galaxies, just with tens of sources with the SKA, you can start to pull out a very strong signal indicating the presence of ionized bubbles. Okay, so that's really interesting. So yeah, I'd encourage you to check out a couple talks about this coming up on Thursday. Okay, so another clever idea that Adam Beardsley put forth a couple of years ago is to kind of admit that we can't precisely determine the ionization state of any pixel in a map, but to say, well, we have these noisy filtered maps. Can we constrain the probability that pixels are ionized on average? And this is really leveraging the fact that the distribution function of pixel values has this interesting, almost binary structure where ionized regions are going to be very negative in the sort of scaled brightness temperature sense. And pixels are either going to be fully ionized, nearly fully ionized, or mostly neutral if reionization works the way we think. Okay. And so what you can do here is you can say, what is the probability, given the brightness temperature value of a pixel I measure, that that cell is ionized? And what Adam showed is that with reasonable certainty, you can identify cells as ionized or mostly neutral, depending on where in reionization you are. So this could be a really interesting way to contextualize JWST fields, for example, or identify fields that would be interesting for study. So we don't usually think of JWST as an ideal cross-correlation partner, given its small field of view, but Eli Visbal has some ideas about this that he's going to tell us about later in this session. Okay, so finally, in just my last couple of minutes, I'll just quickly talk about models. And so I don't think I need to tell this audience that this is a really hard problem, modeling both reionization, but also potentially the messy astrophysics that's giving rise, especially to some of these far infrared lines, for which the relationship between luminosity and star formation rate might be more complicated. So I've overlaid here the box sizes of many state-of-the-art simulations of galaxy formation and reionization. The smattering of them at the top here are all simulations with full radiation hydrodynamics running in line. Whereas the kind of bottom set of these are state-of-the-art galaxy formation simulations with hydro and gravity, but generally are going after low redshift, galaxy scaling laws and this kind of thing. So don't have radial transport, but do have bigger boxes. So for reference here, the size of the Roman HLS, it doesn't have this square shape, but that's about its area. JWST field of view is tiny here, and then 10-degree scale bar indicative of the Harris stripe width. Okay, so not necessarily a great match here. Simulations are simulating relatively small volumes compared to those being probed by observations. And so because of this, there's always trade-offs with modeling. There's really a diverse landscape of models out there. I'm not expecting you to take in any of this information right now, but perhaps it'll be useful for you later. I would encourage you to go to Anastasia's talk tomorrow to hear more about theoretical modeling of reionization. So I'll just highlight a few kind of cross-correlation specific tools that are emerging. One of which is called LimFast, which is built on the semi-numerical code 21CMFast, which is trying to build the machinery to self-consistently forward model reionization, as well as the line emission from the brightest tracers and many more that'll be accessible to experiments now and in the future. And I'm not going to talk about the rad hydro stuff because Rahul will tell us all about that in the next talk. And so I will say that I think there's still room for simpler approaches like halo models. These have been shown to be reasonably accurate in modeling the 21 centimeter background. It remains to be seen whether this is accurate enough for precision inference, depending on what you're interested in. But I think this is worth looking into, both for the auto spectrum and also cross correlations. How am I doing on time, Seth? I think I'm rapidly running out.
You have about 3 minutes.
Okay, so in the last 3 minutes, I'll actually talk about some of my own work that might be relevant here. One might ask, how much do the details matter in terms of the galaxy formation modeling side of things? And so we looked into this last year now. in some detail. And we basically asked a simple question, which is, we often build these models where we parameterize how the star formation rate of galaxies behaves, as a function often of the halo mass accretion rate, okay? So you can go through this exercise of calibrating a model to high redshift luminosity functions to infer basically how efficient star formation has to be per unit mass inflow rate, essentially. And so when you go through that exercise for a few different kinds of doing the modeling, you can match the high redshift luminosity functions, not terribly surprising here. But then if you go and you take your same model and you paint that onto halos from a merger tree from an n-body simulation, which have a much richer diversity in their formation histories, you often end up with biases, okay? And so this is potentially a problem, both in the luminosity functions and the colors. And it's basically because the growth histories of simulated halos are often steeper than the ones we assume in the simplest semi-empirical approach. So we might be able to calibrate this out. This might not be a huge deal breaker. It could result in some biases in parameters of interest, but at least we kind of understand this. But there might be implications for cross correlations here as well. So I'm just showing you a few example ionization fields from these same simulations. And now I'm showing you the positions of galaxies bright enough to be detected in a JWST wide field survey. And then I'm now going to overlay galaxies that would be bright enough to be detected at a Roman high latitude survey. What's interesting about this is you can see as you go, especially to earlier times, often these bright sources do not occupy the centers of the most ionized regions of the universe. These happen to be halos that for one reason or another are undergoing rapid but short-term growth via accretion. So if you assume that the star formation rate traces that growth, that is also where the brightest galaxies are. So this obviously has implications for cross correlations that we might hope to test with future observations. So on that note, I will stop and just emphasize that this is a very rich topic that brings together kind of the power and the complexities of galaxy formation theory and reionization. And I think there's been a lot of great progress on all the fronts. I'm looking forward to seeing how things unfold in the next couple of years. And I'd be happy to take questions.
Great. Thank you, Jordan. That was an excellent review of the topic. Are there any questions? Okay, so we have a question from Caroline Haneka. Thank you for the interesting overview. I was wondering, as for example, Hera and SPHEREx signal to noise is predicted to be low, and we will still have to wait for something like SKA cross CDIM, which shorter term applications to data, for example, Lyman alpha emitter cross correlations, do you think are most promising for Epoch of Reionization cross studies?
That's a great question. And I'm going to in part sidestep the question because I know Paul is going to talk a little bit about this later in this session. So I think, yeah, so I don't want to steal Paul's thunder. I'll set the Hera cross Roman question off to the side for him. I do think some of these stacking analyses could be really interesting. As I was assembling this talk and looking through the literature, I don't know how much detail this has been looked into for Hera or MWA rather than SKA, so that could be interesting. I'm also a big fan of this sort of probabilistic approach, even if you're dealing with these images that have been derived after applying a wedge filter that bear little resemblance to the map you started with. Just being able, I think, to, with some probability, constrain the ionization of different patches of a map. If you, for example, also have a Lyman alpha emitter survey and photometric galaxy survey covering that same region, you might be able to start looking at interesting things like, are the regions where we think they should be more ionized also home to more Lyman alpha emitters, or aren't they? Just those kind of simple, I think, questions could be really, really interesting in the next few years. But again, I think there's a lot to be done here still. And people have been getting creative, and I think that's really cool. We should keep thinking about things like this.
Okay, are there any other questions? Okay, if not, let's thank Jordan. And we now have a 15-minute break. So we will resume at 30 past the hour, and Rahul Kannan will give a talk then. Thanks, everyone. Okay, welcome back, everyone. So our next talk is from Rahul Kannan on predictions for multi-tracer line intensity mapping. Do you want to take it away?
Yeah, thank you, Seth. I'll start sharing my screen. Can everybody see my screen?
Yes.
Okay, great. So thank you for the opportunity to talk about my science in this conference. So I'm Rahul Kannan. I'm a ITC postdoctoral fellow at Harvard. And today I'll talk about predictions for multi-tracer line intensity mapping in the Epoch of Reionization, basically trying to understand the luminosity star formation rate relation for different emission line properties of high redshift galaxies. Okay, so I don't need to go too much into details, but we all know why line intensity mapping is a very powerful tool to study the Epoch of Reionization. So 21 centimeter emission tells us about the neutral gas. Basically, during reionization, it will tell us something about the topology of the reionization process. While emission lines like H alpha, H beta, O2, O3, and Lyman alpha will tell us something about the galaxies that emit the radiation that are responsible for the reionization process itself. So combining both 21 centimeter emission and the nebular emission lines from the galaxies is a very powerful way to study the reionization process and the sources that are responsible for it. There are a lot of instruments that are coming online, that are online right now or about to come online, which are designed to detect emission line intensity mapping from a variety of lines. So there's 21 centimeter, SKA, HERA, for example, CO and C2 from CCAT Prime and COMAP, and SphereX and CDIM will be able to detect rest frame optical lines from these galaxies at a variety of redshift. So just as an example, I show here a SphereX coverage of various emission lines from galaxies, H alpha, H beta, O2, O3, and their redshift coverage. And you can see they detect multiple emission lines from redshift 0 to redshift 7, and even higher redshift if you are looking at lines like O2 and Lyman alpha. So in order to understand or model these different emission lines and the 21 centimeter line, there are a few ingredients that are necessary. First, your model needs to accurately reproduce the reionization history and the topology of the reionization process. The model also requires accurate galaxy formation models, because you need to get the galaxies right in order to get the reionization right. You also need an accurate model for the interaction between the low density IgM and the radiation from the sources from galaxies and black holes. Your model should also be able to accurately predict the emission lines from the galaxies themselves. And in order to do all of this, you need a very high dynamic range. Basically, you need to model the large scale reionization process, which happens on hundreds of megaparsecs or gigaparsec scales. And you need to have resolved predictions of galaxies down to tens of parsec scales. So this is quite a complicated thing to do in most simulations right now. So there have been a lot of efforts to do this using semi-numerical techniques. So I just show a couple of examples here. On the top right here, we show how the emission line properties are usually modeled. So you basically have some functional form of the line luminosity here, H alpha or O3, for example, as a function of halo mass. And then you either paint this line luminosities onto dark matter simulations or semi-numerical dark matter simulations in order to get this. And then you get the bottom panel here, which is on the right is, I think, the H alpha intensity map. On the left is the 21 centimeter intensity map using 21 centimeter fast. So this is currently the best way to look at these kinds of lines. But the question is, can we do better? So that's where the Thiessen project comes in, where we kind of model the large scale reionization process, which we show in the background here, which evolves both the density and temperature of the gas during reionization. and the resolved properties of galaxies. So the inset I show resolved like a mock ALMA and JWST image from this simulation as well. So the question is, can we do better with this line intensity mapping with these kinds of simulations? So as Jordan mentioned in the previous talk, we do not have a very large volume using these simulations, but we can get the properties of the galaxies very accurately. So we'll make advantage of that fact in these with these simulations. So the first point with these Thiessen simulations is that we get the reionization history correct. So that's shown here as a function of redshift, the neutral fraction evolution, and the black are the data points. And these are the different simulations in the Thiessen simulation suite. We not only have one simulation modeling reionization, but we also have different models for the reionization. For example, the orange is a model of reionization where only high mass galaxies contribute. And the green is the model for reionization where only low mass galaxies contribute. And we also have an alternative dark matter model, which is this brown point here. And you can see the effect of these different models in the reionization bubbles. So for example, the high resolution fiducial model. This is a model where only high mass galaxies contribute. And this is a model where only low mass galaxies contribute. And we are basically, what we are showing here is the different bubbles that occur in this reionization process. And you can see that in a model where only high mass galaxies contribute, you have small number of large bubbles. In a model where only low mass galaxies contribute, you have a large number of small bubbles. So you can immediately see that just by looking at the reionization topology, you can kind of get an idea about what is happening in the reionization process. And of course, Thiessen also has the advantage that it also has accurate predictions for galaxy properties, as I mentioned before. So on the left is the stellar to halo mass relation, and the blue is the expected relation that we have, and the black line is the Thiessen result. And you see we lie on this line telling us that the star formation rates are accurate. And on the right here is the mass metallicity relation of the gas in galaxies as a function of different redshifts, and the observational points are shown in black. So we get the stars right, the star formation rate right, and also the metallicities more or less right. So how do you model emission lines? So as I said before, usually people generally assume some kind of a line luminosity star formation rate relation that might be accurate or not. But since we have the right star formation rates and the right metallicities, we can try to model these emission lines properly. So there are a variety of emission lines, like Jordan showed in this previous talk as well. A lot of them arise from these highly ionized H2 regions. Some of them arise from this photodissociation regions. And even more like CO, for example, come from molecular gas. So in order to model this, what we do is we run a grid of cloudy models. So we paint these H2 regions onto these Thiessen galaxies, where for the cloudy models, the stellar ages, that is basically your radiation from the stars, and the metallicities of these H2 regions are self-consistently modeled in the simulations. So the gas, so the metal and the dust content is modeled self-consistently. And using these grid of cloudy models and in combination with Monte Carlo radiative transfer skirt, we can predict not only the photometric properties. For example, here I show a mock JWST image, but you can also predict H alpha emission line properties like H alpha O3 C2 and the IR O3 line at 88 microns. So what you get from this kind of emission line modeling is both the high resolution spectral energy distribution of all the galaxies in the simulation volume, including luminosities for the emission lines that will be detected in the near future from these various telescopes like H alpha, H beta, O3, O2, and C2. So we have to show that the SED modeling is accurate. So we construct, using the SEDs, we construct the UV luminosity function here at different redshifts, 6, 7, 8, 9, and 10. And we show that we produce accurate UV luminosity functions at all these redshifts. showing that the emission line modeling or the SED modeling is kind of accurate. We are also, sorry?
3 minutes.
Okay. We are also able to make accurate predictions for the MUV M-star relation, which is shown on top, and also the beta MUV relation, which is shown at the bottom. So now that we know that the SEDs are correct, we can now look at the L luminosity star formation rate relation that people previously assumed. And we show that, for example, H alpha, the redshift 0 relation given by Kenniket 98 is the red line, whereas the relation derived from these Thiessen simulations is this blue point, the green lines here. And we show that at low star formation rates, we have higher H alpha, mainly because of the low metallicity, the stellar population synthesis models tell us that you have higher Lyman continuum radiation emission. So that's why you have a higher H alpha. And if you look at metal emission lines, we see that we are below the redshift 0 relation, basically because we have lower number of metals. So the main takeaway point from this is that the high Z relations differ from the low Z ones, mainly because of the difference in metallicity. And this tells us the importance of using self-consistent metal and dust emission in order to predict this luminosity star formation relation. So using this luminosity star formation rate relation, we can make emission lines maps for H alpha emission, as an example I show here, and the 21 centimeter emission on the top that I show here. And using these two, we can make we can plot the cross correlation function between the 21 centimeter and H alpha. This is just an example. And this is a model where only large galaxies dominate reionization. We can compare that with a model where small galaxies dominate reionization. And you can see that the transition wave number, that is when the cross correlation changes from negative to positive, the K transition changes, happens at a different place. So you can, and this is just for different reionization models, but with the same ionization state. And if you look at different dark matter model, it also gives you a different transition wave number. So basically, you can plot the transition wave number as a function of neutral fraction. And for different line emissions like H alpha, O3, O388, and C2, each gives you different results. And each different model of reionization also gives you a different transition wave number. So using, because we can do this with these Thiessen simulations, we can place some constraints on both the astrophysics of reionization, for example, the star formation rate, the escape fractions, et cetera, and also on the underlying dark matter model. For example, orange here is a different alternative dark matter model that we use. So I'll just conclude by saying Thiessen, these are large volumes, relatively large volume, allowing us to predict the large scale reionization observables. And we have enough resolution in the galaxies to understand the sources that are responsible for this reionization process as well. The important thing in this talk is that we can make accurate predictions for emission lines based on a grid of cloudy models, and this is an important step forward in modeling emission lines of EOR galaxies. And using these kinds of luminosity star formation rate relation, we can make accurate predictions for the cross correlation between 21 centimeter and the emission lines. And with this has the potential to constrain both astrophysics and cosmology using this new technique. And in the future work, we hope to make this better by modeling emission lines from first principles using accurate ISM models, rather than using cloudy grid models that I discussed here. So thank you.
Thank you, Rahul. So we have a question from Gerald. He says, great stuff. What does the transition scale physically correspond to?
Yeah, so mostly I'll show this here. So the transition scales depends quite a bit on the bubble sizes that you get in these different reionization simulations. So orange is a reionization model where only high mass galaxies contribute, and there the bubbles are larger. So the transition wave number is smaller. Green is a reionization model where only low mass galaxies contribute. So the bubbles are generally smaller, and so your transition wave number is higher. So to first order, the transition wave number just depends upon your reionization model. But as you can see, the slope of the luminosity star formation relation also plays a role. It's a kind of a second order effect. So these are the two things which will decide your transition wave number.
Another question from Ann Hutter. She says, thanks for the talk. When you show the cross-correlation power spectrum for low mass and massive galaxies dominating reionization, what is the ionization fraction of the snapshots you have used there?
So for all of these, the ionization fraction is 50%. So we are looking at the transition wave number at the same ionization fraction, basically. Yeah.
And then she also asked, would you expect that these transition scales become similar when ionized regions merge as the universe becomes more than half ionized?
Yeah, so that's what you see here. So this is the evolution of the transition wave number as a function of the neutral fraction. Initially, the transition wave numbers are quite different, but as the universe gets more and more ionized, the neutral fraction becomes more and more less. All the transition wave numbers kind of go to the same value in these different reionization models. So most of the difference occurs in these early times.
Okay, and one more question from Caroline. She says, thanks for the overview of FASON, a cool endeavor. In the intro, you mentioned we need accurate galaxy formation models. I'm curious how you would define these and what the most important bits are that impact what the final intensity map looks like.
Yeah, so the way I'm defining accurate reionization models is it needs to match most of the observables that you have. For example, the UV luminosity function, the star formation rate densities, the metallicity, the mass metallicity relations, the general things which are important to get galaxies right, even at low redshift. I'm just claiming that you need to get it right even at high redshift. And for these line luminosities, basically what you need is accurate metallicities, accurate radiation field intensities in the ISM, and accurate dust attenuations. So those are the main ingredients to get this kind of right. And if you're talking about Lyman alpha, then it's a bit more complicated because that's a resonant line. So yeah, if you're talking about optically thin lines, then these are enough. But for Lyman alpha, you also need to get the reionization topology and also the line profiles, the blue versus red peak things in order to get it. You need to get that right in order to do Lyman alpha intensity mapping as well.
Great, thank you. So our next talk is from Eli Visbal.
Thank you.
Eli, would you like to go ahead?
Sure, let me start my video, share. All right, so can you see my slides?
Yes, looks good.
All right, well, thank you very much to the organizers for letting me share some of my recent work. Today, I'm going to talk about some theoretical work I've been doing with Matt McQuinn on cross-correlating galaxies measured with James Webb with either line intensity maps in 21 centimeter or other emission lines. So luckily, I don't have to give quite as much intro here because we've heard a lot in some of the previous talks this session. But the point I want to make is that everything I'm going to talk about in this talk relates to both 21 centimeter or any other line intensity map you want to work with. So that could be 21 centimeter, CO, Lyman alpha, H alpha, etc. And as we've heard, all of these lines have the potential to give us lots of information about galaxy evolution, cosmic reionization, and cosmology at high redshift. But another common feature of these observations, which isn't as desirable, is they all have this obstacle that you may have some contamination in your signal due to astrophysical foregrounds. And so in the case of 21 centimeter, you might be worried about residual galactic synchrotron emission that you haven't removed completely. In other intensity mapping lines, such as CO or Lyman alpha, you worry about foreground galaxies that are emitting in different lines, but which are being redshifted into the same observed wavelength. So you're actually measuring sort of a sum of different intensity maps, interloper is at low redshift, plus the signal you really want at high redshift. And so as we've heard today, one potential way to mitigate this challenge is by cross-correlating with galaxies. And so we've heard from Jordan nicely why cross-correlation is a good technique. I've got sort of a little cartoon here to illustrate how I sometimes think about it. So on the right, if we're thinking about, say, taking a Lyman alpha intensity map at redshift 8, we have our Lyman alpha signal we're going after to study the EOR and the galaxies out there, plus H alpha coming from much lower redshifts in the foreground, and the signal that you'll actually measure will be the sum or the superposition of both of these maps. However, then of course, if you cross-correlate with galaxies that you have at the redshift that you're interested in this case, the Lyman alpha redshift, redshift 8, it won't be correlated with the foreground contamination, and you'll just, in cross-correlation, isolate the signal you care about. And so this can be used to confirm your autocorrelation detections, or just study these important aspects of reionization and galaxy evolution if you can't remove the foregrounds even. So that's sort of an introduction to the topic. The project that I want to discuss today is our investigation of the role that the James Webb Space Telescope can play in cross-correlating galaxies with line intensity maps, including 21 centimeters and other galaxy line intensity maps. So, of course, James Webb is highly sensitive to distant galaxies. It's a big telescope. But the challenge in cross-correlation is that it has a very small field of view compared to the intensity mapping experiments that are coming online. So, the James Webb field of view is a few arc minutes, as opposed to potentially many degrees for 21 centimeter or other intensity mapping experiments. And so the question we wanted to answer is, will it be possible to, even though you can't tile the entire sky with the James Webb Space Telescope, if you take a sparse sampling of pencil beams throughout some region where you're measuring an intensity map, and you cross-correlate the galaxies from these sparse pencil beams with the intensity map, can you still recover a measurement of the cross-power spectrum? And if you can, given some constraint on the amount of time on James Webb you want to use, what is the optimal configuration and number of these pencil beams that you would spread across your intensity map to measure the cross-power spectrum with this sparse sampling of galaxies? So essentially, we are trying to figure out the error in measuring the cross-power spectrum if we have a data set that's given by this vector D, which is all of our Fourier modes of our intensity map, plus the overdensities in galaxies in all of our different pencil beams. And we assume that we can measure the galaxies as a function of redshift. We can take their spectra, but we don't worry about their positions within each pencil beam, because the clustering we want to measure is much larger than the scale of the James Webb field of view. And so if you've done some cosmological forecasting in the past, you may be, the go-to tool is often to do a Fisher matrix calculation, and these equations may look familiar to you. You need to calculate the covariance of your data vector, take derivatives of it with respect to the parameter you're trying to measure, in this case, the cross-power spectrum, then you can invert this Fourier or the Fisher matrix, excuse me, and get estimated errors that you would have on measuring that power spectrum. But it turns out this is not what we want to do in this case, because if you were to apply this formula, you're actually including the information from both the autocorrelations in the intensity map and the galaxy survey and the cross correlations. But what we want is actually to only isolate the cross correlation, because we're trying to verify that we haven't been contaminated in the auto, and we don't necessarily trust the auto. We want to just look at the information in the cross correlation. So we need a way to basically measure the error on the cross correlation if you only include the information when cross correlating and not auto correlating. It turns out this has been done previously in the context of cosmic microwave background measurements. I don't have time to go through all the formalism, but we were able to adapt it to this problem that we're trying to address here. Correlating sparse pencil beam galaxy survey with a 21 centimeter survey or intensity mapping survey. And it involves essentially just computing all of the covariances between your galaxy counts in your pencil beams and your Fourier modes in the intensity mapping survey. And so in the paper, which we plan to post on arXiv soon, we've derived all of these formulae to get the covariances and work out this formalism. And so once we've developed this, we can address this question of how accurately can you actually measure across power spectrum when you only have a sparse sampling of galaxies and not, a nice even coverage of the area over which your intensity map is taken. So I'm just going to go over a few examples that we looked at using this formalism. The first is sort of a simple case where we assumed or investigated cross-correlating James Webb galaxies with an intensity map that is completely noise-free. So it's just cosmic variance limited. And this sort of represents the best case you could do for James Webb. So for all these examples, we assume that the galaxies are initially detected with Lyman break, through the Lyman break with NIRCam, and then we follow up on the bright sources and take their spectra. We focus on about redshift 7, just to see how well this procedure could work during the Epoch of Reionization. And for this cosmic variance limited intensity mapping survey, we assume it covers a few hundred megaparsecs on a side on the sky and has a depth of about 150 megaparsecs. And by comparison, the James Webb field of view is only about 10 megaparsecs. So again, it's a pencil beam compared to this large cosmological volume of the intensity mapping survey. And so on the right here, when we apply our formalism, this is what you get if you just put 25 randomly distributed James Webb field of views within this intensity mapping survey, and you integrate for a total of 30 hours on James Webb. So you essentially have an hour per pencil beam throughout this intensity mapping survey and cross-correlate the power spectrum. And you can see you could measure to some reasonable accuracy the cross power spectrum. And because this is, these are the error bars that you would get with our formalism.
2 more minutes.
Okay. So we've also, with our formalism, we can determine how the distribution of these pencil beams affects the signal to noise. So essentially, we've taken these 25 field of views and arranged them in different ways. And what I've plotted is the error relative to a random distribution for having a grid of James Webb pencil beams and what we call a tight distribution where we pack them all together within the intensity map. And you can essentially see that we have looking at this plot, the grid and random, their ratio of errors is 1 almost at all K modes. It's a little different at very low K, but for all intents and purposes, grid and random give very similar constraints. And if you make this tight distribution, you, of course, as expected, lose signal Your noise gets higher for large scales because you can no longer probe the large scales as well, but you do a little bit better on small scales. So you can sort of change your distribution to tune exactly what K mode you want to measure the power better at. You can also look at how well, so that was just for 30 hours. Now we ask the question, given some amount of time, what is the ideal number of pencil beams to put on the sky with James Webb to get the best signal to noise in your cross correlation with a 21 centimeter survey or some other line intensity mapping survey? And so here for this cosmic variance limited case, we've plotted the amount of James Webb galaxies you would detect as a number of James Webb pointings for different times. And if you have too few pointings, you don't see much area, so you don't get very many galaxies. If you have too many, there's not enough integration time, so you don't see very many galaxies either. So there's like a sweet spot of number of pencil beams you want to pick, and those correspond to the best total signal to noise, which is the signal to noise across the crowd, all our power spectrum bins added in quadrature. And the takeaway point from this is, say, if you have 30 hours on James Webb, you would say make 100 pencil beams on the sky and get over a 10 signal to noise in your cross correlation of galaxies in your intensity map. And so I'm reaching the end of my time, but I'll just point out, basically, we've looked at also some more realistic surveys. If you see what you can do with Lyman alpha, we see that with an instrument such as SphereX, if you devote 100 James Webb Space Telescope hours, you can get a signal to noise of 10 by basically tiling 1,000 pencil beams across a large Lyman alpha intensity mapping survey. And so that seems somewhat promising in an achievable amount of James Webb time. Unfortunately, though, when we're looking at Hera, it does take a bit longer to get the signal to noise we would like. So to get a signal to noise of 1 in cross correlation, we found that you really need about 300 James Webb hours and tiled across the sky. And some of the challenges are that Hera scans across a very large area of the sky, to the point that it becomes even, that you don't have as much sensitivity in sort of the field of view where we'd like to pack the James Webb pencil beams together. And so, perhaps other more futuristic 21 centimeter surveys, we could get higher signal to noise more quickly with James Webb, and this is something we're kind of working out right now. So I'm close to time, so I will just leave up my conclusions, and thank you very much for your attention and time, everyone.
Thanks, Eli. We probably have time for one question. Jordan asks, do you know off the top of your head how the depth in each pointing you're proposing would compare to typical integrations we can expect from Parallels? The panoramic JWST program might get a few fields for free.
So I don't know the depths. I can tell you the depths we've looked at correspond to delta Z of half or 1 if you want to get big enough volumes along the line of sight to get enough modes to get good signal. I don't know what those correspond to for the. I don't know what they've chosen for those surveys you mentioned, for those things you mentioned, but yeah, I think it's possible that this type of observation could piggyback on existing things. So if you happen to just study galaxies in a bunch of different fields of view within an intensity mapping survey, you can just steal that data and see if you can cross-correlate it.
Okay, let's thank Eli. And I accidentally swapped the order of Hannah and Eli's talk. Apologies to both of you for that. Hannah, are you available to go next?
Yes, no problem.
Sorry. I'm having a little trouble stopping sharing. Can you just kick me off there? Thanks.
Okay, I hope everyone can see my correct screen.
Yep.
Okay, perfect. So first of all, I just want to thank the SAZERAC committee for giving me the opportunity to speak to you all. My name is Hannah. I work with Adrian Liu at McGill, and today I'll be talking about a new simulation pipeline for 21 centimeter cross correlations. So before I discuss the pipeline, I'd like to just quickly motivate why you would want to develop a tool like this in the first place. And so this project started with the question, can you extract information from 21 centimeter surveys without imposing foreground modeling biases? And so one way you could do this, which has been spoken about earlier in this session, is through cross correlations. And so just to recap from Jordan's talk, if you have two probes A and B, where the signals are denoted by the lowercase letters, and they're both contaminated with noise and foregrounds, and you compute their power spectra, and you assume that all of these components are sampled independently and can factor things out like so, then what you have is the cross-correlation term of interest here. And then you have all of these extra noise and foreground terms, which if you assume that they're all uncorrelated with one another, average down to 0. So this really only happens if you take infinitely many such ensemble averages. And in reality, it's expected that these don't quite average down to exactly 0. And what's more troubling is the fact that the variance, which is comprised of factors of A squared and capital B squared, contain foreground and noise bias that never, even in the idealized case, average away. So we wondered, do the noise and foregrounds really correlate away? What about the effects of instrument systematics? And is there a scenario in which these effects can be detrimental? And so we set out to explore and quantify these effects using end-to-end simulations. And so as a first case study, we've built this pipeline with the intention of simulating 21 centimeter and C2 cross correlations. So before I outline what these simulations entail, I'd like to just explain quickly why we've chosen C2 as our second line. So shown here are simulations from Dimitri et al. 2017, sliced along the redshift direction. And as we move to the right towards high redshift, we see in the top panel, these bright C2 regions in green and red. And in the lower panel, we have these orange H1 regions and these blue ionized regions. So if we superimpose these, it's really easy to see that the bright C2 regions overlap with the ionized regions. So these signals are spatially anti-correlated, the 21 centimeter and C2 that is. And this occurs because carbon is produced and then ionized and then excited in the ISM. And then when it decays, it produces C2 line emission. Another reason why you might want to consider this line is because it's really bright compared to other probes, similar probes at the same redshift. So for example, it's 6 times brighter than CO. So C2, like 21 centimeter, also has its own problems. It suffers from bright foreground contaminants, mainly low redshift line interlopers that consist mainly of CO rotation line transitions from redshift 2. So here is a plot adapted from Chen, Chang, and Bach, where you can slice along an observed frequency and see which lines you'll hit from which redshifts. And the brightness is just here. So now that we know why we should care about C2, I'll move on to discuss our pipeline. So over the past 2 years or so, we've constructed a general framework for simulating 21 centimeter limb cross correlations. And this pipeline simulates instrument responses from virtually any interferometer and single dish telescope. And the instrument parameters and the array layout can be specified for your instrument of choice. So as input, you can either specify the correlation coefficients in the autospectra of your correlated fields, and we produce statistically accurate realizations of these fields that you can use to simulate the cross correlations. Or you can also put in your favorite position space maps from whatever simulation you'd like. So we simulate a host of foregrounds, which are listed here. And as output, we have visibilities, maps produced by each instrument, cross-spectrum window functions, auto-spectrum window functions, and of course, the cross and auto spectra. So for this talk, we've run some simulations of 21 centimeter and C2 observations from redshift 6 to 8, and our instruments are Hera and the Fred Young submillimeter telescope. Today, actually, we've used a miniaturized version of Hera, which consists of 37 elements in the core, as well as a few long baselines. So the shortest baseline is 14.6 meters, and the longest baseline is about 740 meters. And the sole purpose of doing this was just to speed up the computation, but we're currently in the process of running this for the full array. As input, we have these correlation functions, or correlation coefficients rather, which we've interpolated from Gong et al. 2011. And as our input spectrum, which is plotted here on a log scale, which is why it looks a little funny, is a power spectrum that scales as k to the minus 2. So this is our setup, and we've run 4 different scenarios. So the first scenario is to show the correlation of the signals with the noise. Then onto that, we add foregrounds, where in this case, we use only diffuse foregrounds for 21 centimeter. On top of that, we then add bright radio point sources in our 21 centimeter observations. And afterwards, we also simulate an instrument systematic, Hera beam mismodeling. So I'd like to preface these next few slides by saying that what's coming up are not forecasts. These are just examples and illustrations of why we need to start thinking about modeling systematics when it comes to cross correlations. All right. So the first thing that we do is we compute our window function estimated statistics. So the window functions tell us which linear combination of true K modes comprise each observed K mode. So they're basically the transfer functions of your instruments in power spectrum space. And so plotted here on the left is the cross spectrum, which is estimated by our joint window functions, which characterize the joint response from Hera and FIST. And this might look a little funny as a power spectrum because it's negative, but again, this is completely expected to have a negative power because these fields are anti-correlated. And on the right here, we just have the correlation coefficients also produced using these window function estimated spectra. And so now for the rest of the talk, I'm just going to pick one redshift bin and then add systematics to this one redshift bin. And the only reason I'm doing this is to make this easier to see, but the evolution of adding these systematics was largely the same for all of our bins. So this bin in particular was just centered at redshift 6.75. So we start with our window function estimated statistics, and ideally this is what we'd like to measure. But if we add some thermal noise to both of our instruments, we see that that's in fact not what we measure. So while the large scale modes remain relatively intact, we see that on these smaller scales, we start to get these correlations fluctuating between positive and negative due to the noise terms. And so this positive negative fluctuation is expected because this is what you would expect from something that is correlating down as a function of realization. So now if we add our foregrounds, we see that things get a little bit more crazy. So on these large scales, the foregrounds completely dominate. These are mostly due to synchrotron emission in our 21 centimeter maps. And then again, we're seeing this fluctuation on the smaller scales, which we expect would correlate away at some point. So now adding bright radio point sources. So I'll be adding some bright radio point sources on the order of 10 to the 4, 10 to the 5 Kelvin into the 21 centimeter field. And so this is a little cartoon of where I've placed these point sources. And so they're actually not in the patch that we're simulating, which is denoted by this red square. But what they are still within the beam that we're modeling. So these sources are outside our field of view, but still within the beam. And when we add these sources, we see that we have an additional bias due to these point sources that presents itself in our spectra. And so some of you may be thinking, well, what does this all mean? Is it all over for 21 centimeter limb cross correlations? These all look awful. But the answer to that is no, not yet, or we don't think so. As I said earlier, these are not forecasts. These are purposefully pessimistic examples of why it's important to take these effects into account. And we do expect that if you do these sorts of simulations with the full instrument specifications, with an area that's larger than 4 square degrees, that you will be able to see those noise and foreground terms start to correlate away, and that you will be able to place some sort of constraint on the cross spectrum. And that's what we're currently continuing to work on. So very quickly, I just want to touch on the beam mismodeling.
About a minute and a half.
Perfect. So the beam mismodeling that we simulate is where we misassume the beam width of our Gaussian beam by 10%. So we have our instrument actually performing the observations with this beam, but then in our analysis, we mischaracterize the beam as this, and this is simply a cartoon. So the first issue that you run into with this is that you produce the wrong power spectrum estimates because you're estimating your spectra with window functions containing the incorrect beam model. So next, we simulate our observation with beam mismodeling. So this orange line is the cross spectrum computed from a map whose visibilities were computed with a true beam, but then was mapped using an estimator computed with the wrong beam. And it may seem surprising that even with these beam errors, these two lines are so similar. But in fact, over the 4 square degree patch that we were viewing here, the beam response was roughly the same. Where we really start to run into issues here is when we add bright point sources that were well within the true beam, but that were assumed to be basically completely attenuated with the wrong beam. And you can see that it incurs a huge bias on our spectrum. And this example is just here to showcase that while one systematic alone may not pose a large threat, that there are these synergies between systematics that can produce detrimental effects. And this is really just to hammer home the point that we need to start simulating all of these systematics together. So just in summary, cross correlations are an avenue for extracting cosmological information from heavily contaminated data sets. Nonetheless, we still need to think about systematics. With these end-to-end simulations, we can more faithfully forecast the biases imposed by these systematics. And coming soon from us are a host of improvements on our pipeline. So full experimental design parameters. We're going to be including RFI flags and statistics from HERA, calibration errors, baseline non-redundancy errors, and of course, forecasts. So if there are any questions, I'd be happy to take them now.
Thanks, Anna, and definitely looking forward to that. So there is one question from Gerald. He says, thanks for an illuminating presentation. How can you characterize your 21 centimeter signal with only a power spectrum, given that it is strongly non-Gaussian? Or in other words, how do you produce the distribution of your ionized bubbles in which the C2 galaxies live?
Right. So the way that we produce these fields from our correlation functions and an input spectrum is through a similar method that you can find in Pagano and Liu, I believe 2020, which is using phase shifts in Fourier space. So what we do is we take one field which has a known power spectrum. So you can take, for example, a 21 centimeter power spectrum and then decorrelate and then produce a realization by sampling that power spectrum in Fourier space and then inverse Fourier transforming. So what we do is once we produce one of these fields using the correlation information from those correlation coefficients, we compute a parameter from which we can draw phases, which we apply to the original Fourier field which produce a field that contains the correct correlations. So we're not actually simulating the morphology of these fields, but we're simulating fields that statistically contain the correct correlations. I'm sorry if that was a bit long-winded, but this will all be outlined in a paper very, very soon. And it's a great way to very quickly simulate fields that have the statistics that you care about.
Thanks, Hannah.
Thank you all. So I'll stop sharing.
Okay, our last talk of the session is Paul Plante. Paul, do you want to take it away?
Sure. Thanks very much. I'd like to thank the organizers for putting together this excellent session on cross correlations. As we've talked about, there's definitely a lot to be excited about and lots of really exciting updates that folks have been sharing. So just to kind of cap off this session, I'll be talking today about 21 centimeter cosmic microwave background and galaxies during reionization, 3 sides of the same coin. So my name is Paul Plante. I'm a postdoc at UC Berkeley right now. And I'm really excited to share some of these updates with you today. So just to kind of set the stage a little bit, we've already talked at length about kind of the picture of reionization that we have. So I'll be brief here, but people have not yet talked about the CMB, at least in depth. So I feel like I can use that as my on-ramp here. So basically we have galaxies and ionized regions from reionization, and then the photons from the CMB, from the surface of last scattering, as they propagate toward us, some of them will inverse Compton scatter off of free electrons in the IgM that come from the ionized regions and receive a kick based on the peculiar velocity of those electrons in the IgM. And so this is known as the kinetic Sunyaev-Zeldovich effect, or KSZ, because that's kind of a mouthful. And just like galaxies and ionized regions, we expect there to be encoded in that signal some hints about the ionization history, the duration, the timing of it, kind of in this signal. So one thing to note is that like line intensity maps, it's an integrated quantity. So you basically just get a 2-dimensional map, but you can still try to do cross correlation with a 3-dimensional tracer like the 21 centimeter signal, although there are challenges associated with that, which I'll talk about in a little bit. So the way that we kind of forecast some of these expected signal levels is by doing semi-numeric simulations of reionization. So just to kind of show people kind of the types of boxes that we're working with. These are relatively large, about 2 gigaparsec on a side, but we're able to self-consistently generate the relevant observables that we care about here. So on the left, we have a simulated KSZ map, and on the right, we have a corresponding 21 centimeter map. And then you could also play the same game with a galaxy field. So we've talked a little bit about JWST galaxies. In this case, we're looking more for a wide field galaxy survey like what we would have with the Roman Space Telescope. And then the idea is that you can cross-correlate these different fields together. So in part 1, I'll quickly talk about cross-correlating KSZ and 21 centimeter. In part 2, I'll talk about 21 centimeter in galaxies. And then the third leg of this triangle is interesting in its own right, KSZ cross galaxies. But for the purpose of this talk, it's a little outside the scope. But if you're interested, we recently looked into what forecast levels we expect for that signal. So just to start with part 1, we are interested in cross-correlating the 21 centimeter and the KSZ signals, but unfortunately, it's a little bit tricky. And the reason for that is because the KSZ, like I mentioned, is sourced by the peculiar velocities of this ionized gas, these free electrons. And basically, these bubbles are equally likely to be moving toward or away from us. So on the right here, I've got a visualization of different components of the KSZ. So the largest patches that your eyes might be drawn to that are kind of these degree scale hot and cold patches, they're actually sourced by large scale velocity fields. So they're not interesting for ionization. We don't really learn anything about reionization from those features. So what we're more interested in is the top right panel, And you might be able to see that you kind of have red and blue blobs that are kind of right next to each other. So if you just do the naive cross correlation, the fact that they're positive and negative, the signal basically falls out. You have this catastrophic cancellation that you have to do something about. So something you could try is to square the K as E fields after you filter out the primary CMB, which has been looked at before. I'll be talking a little bit about the cross bispectrum, which kind of allows you to target specifically which modes you're interested in. And by using 2 copies of the K as E field, you can get around this cancellation. And I'll be talking specifically about a forecast for the Simons Observatory, which is a current / next generation CMB experiment being constructed in Chile right now, and Hera, which we've talked a lot about and heard a lot about. So just to kind of, I'll go quickly through this part. If you're interested, you can read more in the paper. So we're looking specifically at the squeeze triangle configuration. So what this means is that you have one short side, which we use for the 21 centimeter field. So that probes small K modes, which is large scales. And then we have 2 K as Z legs of the triangle, which are large K, which probe small scales. So essentially what we're doing is we're looking, one way to think about this is it's a conditional probe of the small scale ionization power spectrum based on the large scale 21 centimeter field. So that, because that's kind of what the squeeze triangle tells you in a statistical sense. And one thing we found is that this statistic is very responsive to the ionization history. So in this figure on the right here, the top panel is a few different ionization histories that we looked at in our study. The middle panel is the resulting bispectrum amplitude. And then the bottom panel is the K as E window function, which is important for computing the cross correlation. So just to look at the middle panel, one thing to note is that there's a negative signal before the midpoint and a positive one after. That kind of makes sense given what the probe is telling you. I'll kind of skip through the details, but it's all there if you're interested to learn more. And then the other thing to note is that the size of the signal depends on the duration, which again kind of gives you a hint at a way to, if you were to measure this in the future, you could invert this and say, okay, I can learn about the ionization history by matching the window of my 21 centimeter signal with to maximize that response. So there's a lot more details that I'll be skipping over, and the main takeaway is that there's a significant detection if you ignore the 21 centimeter wedge. So we've talked a lot about these foregrounds. They pose a problem for these types of intensity mapping measurements for the same reason that the modes you're most sensitive to are very low in K parallel space, which are exactly the ones that are most contaminated by your 21 centimeter foregrounds. So if you just look at the statistical uncertainties of SO and Hera, you get something like a 20 sigma detection, which is excellent. But in practice, it'll be really difficult to achieve. So just a quick takeaway, the signal is relatively large. It's, booming. If you could get around the foregrounds, it's definitely worth measuring. And something like SKA might help, but it's not going to make the problem go away entirely. So one potential way around this could be using an even higher point function, like a 4-point function, maybe squaring the 21 centimeter field. But I'll kind of leave that there for now. It's definitely worth investigating in the future. So now part 2, which is more exciting, I'll talk about 21 centimeter across galaxies. So Jordan kind of foreshadowed this work a little bit, where we're looking specifically at correlation between Hera and the Roman Space Telescope, specifically the High Latitude Survey. So Roman is scheduled to fly in the mid-2020s. And it's as part of it, it's going to have this high latitude survey that's expected to observe about 1 million galaxies above redshift 6. And what we're interested in specifically is Lyman alpha emitters as part of this survey. And so the goal here is to compute the cross spectrum in 3D. And by computing it in 3D, then you can avoid this problem of the 21 centimeter foreground cancellation. So this might look familiar from Jordan's talk, but basically we can do this because the footprints of Hera and the Roman HLS overlap in the plane of the sky. So it's not the entire HLS footprint, but there's about 500 square degrees of overlap, which is more than enough to our detection, as we'll see. So Jordan alluded to this a little bit in his talk, but as it's been a common theme in the other talks, modeling galaxies is really important, and understanding how they fit in with your 21 centimeter field is also important. So for this kind of first effort, we just use a linear bias model, and we investigate two different ways of getting this bias. So Jordan mentioned the blue tide simulation, and then these semi-empirical models that we developed. So they give you similar bias values, which are huge. Sidebar to point out, bias values about 10 or so. So these are very highly biased sources, but there's a slight difference maybe at the 20 or 30% level. So, and then you also want to self-consistently compute the bias and the number density of galaxies. And then kind of not surprisingly, if you go to fainter galaxies that are hosted in less massive objects, you have a lower bias value, but you have a larger number density. So it's kind of a trade-off. And as we'll see, deeper is better.
2 minutes.
So then, thank you. Then just to talk quickly, we look at the experimental uncertainty for 21 centimeter power spectrum. It's driven primarily by the distribution of your baselines. So for Hera, that's good for us because we're very sensitive to the low K modes where we get most of our sensitivity. For galaxy surveys, you have both the number density and then your redshift uncertainty. So basically, the important caveat there is that we need spectroscopic redshifts to do this. Photometric redshifts are not good enough, but we expect to get spectroscopy for most of these objects in the HLS. So that works out well for us. And then I'll skip quickly through this because I want to get to the main takeaway. But basically, the signal is we measure it or we model it in terms of K parallel and K perpendicular, because that explicitly allows us to include the wedge and kind of different levels of foreground contamination. So we expect individual modes to have relatively low signal to noise, below 1, but by averaging together over our full Fourier space and our full redshift coverage, we're able to get a relatively significant detection. So we also model some of these parameters, such as the uncertainty of redshifts and what fraction of galaxies in the HLS we expect to be Lyman alpha emitters. And basically, in all these cases, we eke out a relatively significant detection, which is exciting. So this time we actually have a significant detection, which is great. If you kind of make some default assumptions about your observations, it's about a 2 sigma detection. But if you can go deeper with the HLS, then you can actually get more bang for your buck. So if you go just 1 magnitude deeper for your object, or for your limiting magnitude for your objects, you increase your signal to noise to about 4. If you go 2 magnitudes deeper, you go to about a 9. That's what this figure on the right is showing, your sensitivity as a function of your magnitude. And then the other way you can really improve your sensitivity is by working in the wedge a little bit. So throughout all this, we've assumed kind of a pessimistic horizon cut, but if you can get some of that sensitivity back, then you can boost your signal to noise. You can see for the diamond, you can get a signal to noise of about 20, which is then you're kind of cosmic variance limited. So that's about the best you could hope to do. So just quickly, I'll leave these conclusions up and I'm happy to answer any questions. Thanks very much.
Thanks, Paul. Are there any questions? And I guess so Gerald asks, are your LAEs affected by neutral IgM?
That is a very good question. Yes. So you might expect there to be some intervening absorption if the LAE is, say, close to the edge of one of your bubbles. We're kind of hand waving that away by saying because these galaxies are expected to be so highly biased that they're sort of unlikely to be near the edge of these objects, but kind of the way that we're treating this Lyman alpha emitter fraction is, basically a number that we dial between, say, 1% and 100% of the objects are LAEs. So you could imagine just, dialing it down a little bit, if you like, to say, oh, we missed some of these LAEs that were kind of close to the edge of the bubble in some sense. And so just to go back quickly, the purple dots is the pessimistic LAE. So your signal to noise is less than 1 if you only have 1%. But if you can go deeper, then you have you can see something like a 1 to 2 sigma detection. So so basically the point is if you go deeper, then you can overcome some of these other observational challenges.
And Stefan Airage asks, thanks for the nice talk. Is there possibly anything useful to learn from the 21 centimeter KSZ Galaxy bispectrum?
That is a very interesting question that I haven't thought about. I will sort of sidestep the question and just say that the reason where you get this cancellation that I mentioned at the top is if you only have one copy of the KSZ field. So you either have to have 2 copies in your bispectrum, or you would have to square the KSZ to do like a cross spectrum. So you could imagine maybe doing the KSZ squared 21 centimeter Galaxy bispectrum. So all that to say though, that is very interesting and might be worth thinking about more in the future, but I personally haven't thought of it yet, but it's a very cool idea.
Okay, thanks, Paul. And I think that concludes the session. So thank you to all of the speakers for the excellent presentations. And also thank you to the participants for the thoughtful questions.
Yeah, I think that concludes the day. Thanks, everyone. Thanks, Tess, and thanks to the speakers. So we'll resume tomorrow at 9 a.m. GMT with the first session about analytical and numerical modeling of the signal, which will be chaired by Sambit Kiri. So see you then. And don't hesitate to ask more questions on Slack. Bye-bye.